In this lecture, we are going to describe the ideas of supremum and infimum of a set of real numbers. This idea of supremum is similar to maximum of a set of real numbers. The idea of infimum is similar to minimum of a set of real numbers. In addition to supremum and infimum, we shall also discuss the notions of sequence in Rn or sequence of vectors and their convergences. Neatly, the topics of discussion in this lecture are the following. We will start our discussion with the notions of supremum and infimum of a set of real numbers. Then we will move to the notion of sequence of points or sequence in Rn. Thereafter, the notion of convergence of a sequence will be talked. In identifying convergence of a sequence of points, we commonly require a prior knowledge about the limit of the sequence. However, if it is difficult to guess the limit of a sequence, we can employ an idea called Cauchy sequence in Rn. We will get to know that a sequence of points or a sequence in Rn is convergent if and only if the sequence is a Cauchy sequence in Rn. After discussing the idea of Cauchy sequence in Rn, we will discuss the notion of subsequence of a sequence in Rn. Finally, the ideas of limit superior and limit inferior for sequences of real numbers will be discussed. So here the first agenda and the last agenda are for elements in R. However, these three agendas in between are for elements in Rn. These first and the last agendas require the collection of elements to deal with is such a collection that any pair of elements of this collection is comparable. That is, if A and B is a pair of elements, then either A is less than B or B is less than A or B is equal to A. Such a comparability property between any pair of elements is not there for a collection of elements taken from Rn with n greater than equals to 2. For example, take two elements, say 1 2 and 2 1 from the R2 plane. Then we see that we cannot identify which one is bigger, this point or this point. So the concepts of greatest and least element cannot be talked for a collection of elements in Rn with n greater than equals to 2. As the first and last agenda require some kind of greatest and least element, we consider to talk those ideas only in R, not in Rn for n greater than equals to 2. Well, let's start our discussion with the notions of supremum and infimum of a set of real numbers. Before starting with these two ideas, let us recall quickly what have we done in the previous lecture. In the previous lecture, we have discussed a few notions from the sets in Rn. Specifically, we have discussed the notions of neighborhood, open and closed balls, limit point and interior point of a set. With the help of interior point, we have defined the idea of an open set. With the help of the notion of limit point, we have defined the idea of a closed set. The ideas of bounded set and compact set were also talked. We got to know that a set in Rn is compact if and only if the set is both closed and bounded. We ended up the previous lecture with the ideas of label sets and epigraph for a given function of several variables. Let's start discussion with the first agenda of this lecture, that is the idea of supremum and the idea of infimum for a set of real numbers. I guess we all have a rudimentary knowledge about maximum and minimum element of a non-empty subset of real numbers. An element, say capital M, in S is called a maximum element of the set capital S if for every element x in capital S we have x less than equal to capital M. Similarly, an element, say small m, in the set capital S is called a minimum element of the set S if for every element x in S we have x greater than or equals to small m. Now, having known this definition of maximum and minimum elements of a set capital S, let me ask you a question. What is the minimum element of the set capital S, which is the collection of one, half, one third, one fourth, so on? That is, it is the collection of all the numbers of the type 1 over n, where small n is a natural number. To find a minimum element, you may then go for locating all these elements of the set capital S in the real number line and then find that the elements are this 1, then half, then one third, one fourth, one fifth, and so on. So what is the least possible element of all this collection of elements in the set capital S? The element 0 is seemingly the minimum element of the set capital S, but 0 cannot be a minimum element of the set because a minimum element must be an element of the set capital S. Then how do we achieve this seemingly minimum element 0 of this set capital S? To achieve this seemingly minimum element, we approach in the following manner. We at first define a notion called lower bound of a set, which is defined as follows. Consider a non-empty subset of the real number set, then a real number, say small l, is called a lower bound of the set capital S if for any x in capital S we have x bigger than or equals to small l. Similarly, the notion of upper bound can also be defined for a non-empty subset of real numbers, say capital S, if there exists a real number, say small u, for which we have x less than or equals to u for all x belonging to capital S, then the number u is called an upper bound of the set capital S. A set capital S is called bounded below if it has a lower bound. Similarly, a set capital S that has an upper bound is called bounded above. A set that is both bounded above and bounded below is called a bounded set. Therefore, in order to say that a set capital S is bounded, we must have an upper bound of the set capital S as well as we must have a lower bound of the set capital S. Thus, a set capital S is bounded if and only if there exists a lower bound and an upper bound of the set capital S. So if we locate the elements in capital S in the real number line, then we will find that the elements in capital S are located in such a manner that they are never exceeding small l on the downside and small u on the upper side. Now, by considering the distance of u from origin and the distance of l from origin, take the maximum of these two distances, denoting that maximum distance by k, we can identify that the elements in S are lying in between minus k to k, and hence a subset of the real number set is bounded if and only if there exists a non-negative real number k such that absolute value of x is less than or equal to k for every x inside the set capital S. Now this definition of boundedness of a set is defined for a subset of the real number set. If we have a subset of Rn, then we define its boundedness in a similar fashion, that instead of considering this absolute value of x, we consider norm of x, and a set in Rn is called bounded if there exists a non-negative real number k such that norm of x is less than equal to k for every element x in the set capital S. Here I would request you to check that this definition of boundedness of a set in Rn is equivalent to the boundedness definition that we have defined in the previous lecture. For the time being, let us now keep aside this boundedness notion for the sets in Rn, and let us get back to our definition of bounded above and bounded below sets of real numbers. We see that if a set is bounded below, then there exists a lower bound of the set, say small l, and once small l is a lower bound, then we see that every element inside the set is always bigger than or equals to the number small l, and hence every element of the set capital S is also bigger than L minus 1 and also bigger than L minus 2 and so on. So if L is a lower bound of a set capital S, then all these numbers L minus 1, L minus 2, L minus 3, or even any number smaller than L is also a lower bound of the set capital S. The greatest among all these lower bounds of the set capital S is called greatest lower bound of the set capital S. But how do we identify that a lower bound is greatest among all the lower bounds? We can identify in the following manner, that a real number, say capital L, is the greatest lower bound of the set capital S if capital L is a lower bound together with the condition that any number bigger than capital L is no longer a lower bound of the set capital S. The second condition of greatest lower bound says that if I consider a number slightly bigger than capital L, that is, let's suppose capital L plus a number epsilon greater than 0, then this number L plus epsilon is no longer a lower bound of the set capital S. That means there exists at least an element of the set capital S which does not allow the number L plus epsilon to be a lower bound of the set capital S. That means for any given epsilon greater than 0, there exists an element y in the set capital S which is smaller than the number L plus epsilon. So we neatly write the definition of greatest lower bound of a bounded below set as follows. Consider a non-empty subset of the set of all real numbers. A number capital L is said to be greatest lower bound of S if we have two conditions, that the number L is a lower bound that is x is greater than or equals to capital L for all x in S, and for any positive epsilon there exists an element small y in the set capital S such that y is smaller than L plus epsilon. Now, having known this definition of greatest lower bound, let us now get back to this problem where we were trying to identify the minimum most element of the set capital S. We have figured out that the element 0 is a seemingly minimum, but 0 is not really a minimum of this set. But we notice that this element 0 is a lower bound of the set capital S, as well as whatsoever element slightly bigger than 0 you consider that is no longer a lower bound of the set, because for any given slightly bigger element than 0, let's suppose epsilon, we see that there is a sufficiently big natural number p for which we get 1 by p is smaller than epsilon, and thus whatsoever small epsilon you choose, this epsilon can never be a lower bound of the set capital S, and hence 0 is the greatest lower bound of the set capital S. This greatest lower bound here is not a minimum element of the set, but we call it as an infimum of the set capital S. We call the greatest lower bound also by the term infimum, or in short INF of the set capital S. There is also a common abbreviation of the greatest lower bound. We abbreviate it by GLB. Now here this notion of greatest lower bound is for a bounded below set. There is also a similar concept for bounded above set, that is known as least upper bound. Mathematically, we define least upper bound of a set of real numbers as follows. For a non-empty bounded above subset of real numbers, say capital S, a real number capital M is said to be least upper bound of the set if capital M is an upper bound of the set, and for any given epsilon greater than 0 there exists an element y in capital S such that y is bigger than capital M minus epsilon. The term least upper bound is abbreviated as LUB, and LUB of a set capital S is also known as Supremum, or in shorthand sup of the set capital S. Let us now quickly consider a few examples in which we will identify supremum and infimum of the given sets. Let us consider the sets. The first one, S1, is the collection of all real numbers of the type 1 upon n, where n is a natural number. Consider the second set as the collection of numbers of the type n to the power minus 1 to the power n, where n is a natural number. Consider the third set S3 as the set of all real numbers whose square is less than or equals to 1. For the set S1, we have already identified that its infimum, or the greatest lower bound, is equal to 0. But what about the supremum? For the collection of elements in S1, we see that the number 1 is the maximum most element of the set S1, and therefore this number 1 will act as the least upper bound. Supremum of the set S1 is equal to 1. For the set S2, we see that it is the collection of the real numbers. The first is 1, the second element is 2. For n equals to 3, you will get 1/3, then 4, then 1/5, then 6, 1/7 in this manner. So here for this set S2, we see that there is no upper bound, and hence S2 is an unbounded above set. For an unbounded above set, we define its supremum as positive infinity. Similarly, for a set that is unbounded below, we define its infimum as negative infinity. For the set S2, we see that it is bounded below, and now I ask you to figure out its infimum as the number 0. For the set S3, its infimum is equal to -1 and supremum is equal to 1. From these all definitions of supremum, infimum, maximum and minimum, we see that if the least upper bound of a set is an element of the set, then the supremum of the set is nothing but the maximum element of the set. Similarly, if the greatest lower bound of the set is an element of the set, then the infimum of the set is nothing but the minimum element of the set. Now here, while referring this least upper bound of a set, quite often I have used the article the least upper bound of the set. Here I would like to ask you a question. Is the usage of this article the appropriate for referring the least upper bound of a set capital S? That is, mathematically I ask you to figure out the answer of the following question. Can a non-empty bounded above set have two distinct least upper bound or supremum? The answer is obviously no. You please figure out why. And therefore the usage of the term the supremum or the least upper bound of a non-empty bounded above set is an appropriate usage. Now in the next we shall move to the next agenda of this lecture, the topic of sequence of points or sequence in Rn. You know, this notion of sequence in Rn is of utmost importance in this course, because in any numerical algorithm, to find a solution of an optimization problem, we will generate a sequence in Rn by some numerical algorithms, and then we will go for checking whether the sequence is converging to a point at which a necessary optimality condition is satisfied. I guess any student attending this course has some ideas of sequence and limits, as those are introduced in high school elementary calculus. By a sequence of real numbers, we mean an ordered list of numbers. That means we have a first element, say A1 in the list, we have a second element in the list, say 2, we have a third element, say A3, and so on. This ordered list of numbers is commonly denoted by, in a compact manner, just by AK, where K ranges in the set of all natural numbers. That means K is from 1, then 2, 3, 4 and so on till infinity. In a more simplified manner, if there is no confusion, we commonly do not write this range of K, we simply write second bracketed AK to mean a sequence. Note that a sequence is not just a collection of real numbers, but an ordered collection of real numbers A1, A2, A3 and so on. Taking into account A1 is the first element A2 as the second element, A3 as the third element, and so on. Mathematically, a sequence of real numbers is presented by a function from the natural number set to the real number set, where the value of the function for the natural number small n is equal to an. Similarly, a mapping or a function from the natural number set to Rn is called a sequence in Rn. In our course, in order to distinguish a sequence in Rn from a sequence in R, we will present any sequence in Rn by a superscript manner. That is, the value of the governing function f of a sequence in Rn will be presented by x superscripted k, where k is a natural number. Here this k has not to be confused with power of the variable x. It is just a denotation to present a sequence in Rn for n greater than equals to 2, and for a sequence in R we will use a subscripted k. So this superscripted indexing is for n greater than equals to 2, and subscripted indexing will be used for n is equal to 1. Now next we will discuss the idea of convergence of a sequence. Well, before discussing the notion of convergence of a sequence, let me quickly mention the notions of monotone increasing and monotone decreasing sequence for sequence of real numbers. A sequence of real numbers, say AK, is said to be monotonic increasing, abbreviated as MI, or by the shorthand an upwards arrow, if consecutive elements of this sequence are such that a previous element AK is smaller than or equals to a later element AK plus 1 for every k in the natural number set. Likewise, a sequence is said to be monotone decreasing, abbreviated as MD, and presented by a shorthand, a downwards arrow, if AK plus 1 is less than equal to AK for every index k in the natural number set. A sequence AK is said to be strictly monotone decreasing if the inequality here comes up with a strict inequality. Similarly, a sequence AK is said to be strictly monotone increasing if the inequality here comes up with a strict inequality. Now we shall talk about convergence of a sequence in Rn. For the convergence of a sequence in R, we all know that a sequence, say AK, of real numbers is said to be convergent and converges to some number, say the real number A, if we realize that the positions of the terms of the sequence AK in the real number line are such that when the index k gets larger and larger, the sequential elements AKs are clotted or clustered or gathered around the value A. That means almost all terms except only a finitely many of the sequence AK comes arbitrarily closer to the real number A. That means you consider any small neighborhood of the real number A. Let's suppose A minus epsilon to A plus epsilon for any given however small number epsilon greater than 0. This interval A minus epsilon to A plus epsilon contains all the terms AKs after certain index number say k greater than or equals to k naught. So precisely we say the sequence ak converges to the real number a if for any given epsilon greater than 0 there exists an index number k naught such that absolute difference between ak and a is less than epsilon for all k greater than or equals to k naught. Similarly, for a sequence in Rn, we define the convergence in the following manner. A sequence, say xk in Rn, is said to be convergent if there exists a limit, say x bar, in Rn such that for any given epsilon greater than 0 there exists an index number, say capital N, for which the sequential terms xk's after the index number capital N lie inside the open ball having center x bar and radius epsilon. So if we look at the locations of the sequential terms xk's which is converging to x bar, we shall see that the locations of first n minus 1 many elements, that is x1, x2, x3 till xn minus 1 may be outside this open ball, but after the index number capital N, the sequential terms will be inside this open ball, and when the index k is substantially large, then we'll see that the sequential elements will get clotted or get clustered towards the location of x bar. We write this observation regarding convergence of xk by the distance of xk from x bar less than epsilon after the index number k is bigger than or equals to capital N. We say this vector x bar as a limit of the sequence xk, and we write this entire phenomenon by the shorthand that xk converges to x bar as k tends to infinity. If there is no confusion, sometimes we will skip writing as k tends to infinity, or by limit k tends to infinity xk is equal to x bar. Here is also, if there is no confusion, on the bottom of this denotation limit we will not write k tends to infinity. A sequence that is not convergent will be referred as a divergent sequence. Now let me quickly present a few results related to convergence of a sequence in Rn. The first result towards this is the following. Let's suppose we are given a sequence xk in Rn by xk is equal to x1k, first component of xk, x2k, which is the second component of the vector xk, till the nth component of the vector xk is xnk. This sequence is convergent if and only if all these component sequences of real numbers x1k, x2k, xnk are convergent. More precisely, the sequence xk is convergent and converges to the vector x bar, which is given by the components. Say first one is x1 bar, second component is x2 bar, and till xn bar if and only if the sequence of real numbers xjk converges to xj bar for all j equals to 1, 2 till n. So convergence of a sequence in Rn can be determined by the convergence of the component sequences. Proof of this result is very simple. I'll just sketch out of the proof. Notice that for the forward part, let's suppose the sequence xk is converging to x bar. Then by the definition of convergence of a sequence, for any given epsilon greater than 0, there exists an index capital N for which the distance between xk and x bar is less than epsilon after the index capital N. Now, as usual, as I said earlier, if we use this norm as the Lebesgue norm or the Euclidean norm, then this inequality gives us positive square root of x1k minus x1 bar square plus x2k minus x2 bar square plus so on till xnk minus xn bar square of it is less than epsilon for all k greater than equals to capital N. Now we see that for every j ranging from 1 to till n, we have xjk minus xj bar, absolute value of it is less than or equals to positive square root of this entire expression, and hence we get that the sequence xjk is converging to xj bar for all j's. Now for the reverse part, let us suppose all these component sequences xjk's are converging to xj bars and start with some given epsilon greater than 0. As xjk is converging to xj bar corresponding to epsilon 1 as epsilon divided by under root of n, which is a positive quantity, we get a natural number capital Nj for which we have the absolute difference of xjk minus xj bar less than epsilon by root n for all index k greater than equals to nj. Now consider capital N as the maximum of all these index numbers n1, n2 till nn. Then we see that we have xjk minus xj bar less than epsilon by under root of n for all k greater than equals to capital N, and this phenomenon is true for every j is equal to 1 to till n. Now all these n inequalities together gives us the norm of xk minus x bar. The square root of all these sums is less than epsilon for all index k greater than equals to capital N, and therefore the sequence of points xk converges to the point x bar. Now let me move to the next result, which states that a convergent sequence of points cannot have two different limits. That is, a sequence xk in Rn can have at most one limit. This result is again very easy to perceive because a sequence is either convergent or not convergent. If not convergent, then there is no question of having a limit. But if convergent, then we have to show that we cannot have two different limits of the sequence xk. On contrary, let's suppose the sequence xk is converging to x bar as well as x bar dash say. Now for any given epsilon greater than 0 corresponding to this convergence, we will get an index say capital N bar for which the distance between xk and x bar is less than epsilon by 2 for all k greater than equals to n bar. Similarly, for this convergence, we get an index number n bar dash say for which norm of xk minus x bar dash is less than epsilon by 2
for all index k greater than equals to n bar dash. Now consider capital N as maximum of these two indices n bar and n bar dash, then we see that both these two inequalities are true for every k greater than capital N. Now from these two inequalities we see that the distance between x bar and x bar dash is less than or equals to, by the triangle inequality, norm of x bar minus xk plus norm of xk minus x bar dash. Or specifically, let us consider norm of x bar minus xn plus norm of xn minus x bar dash, which is further less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. So we see that the distance between x bar and x bar dash is smaller than any arbitrary small quantity epsilon, and hence we certainly have x bar identical to x bar dash. Here you please figure out why 0 less than equal to this norm less than epsilon will certainly imply that x bar is equal to x bar dash. Now let me move to the next result, which states that a convergent sequence is bounded. This is again very easy to perceive. Here it is given that the sequence xk is convergent. So let us suppose the sequence xk is converging to x bar, then corresponding to epsilon is equal to 1, there exists a natural number, say capital N, for which we have norm of xk minus x bar less than 1 for all index k greater than equals to capital N. Now this inequality gives us norm of xk is less than or equal to norm of xk minus x bar plus norm of x bar, which is less than 1 plus norm of x bar for all index k greater than equals to capital N. Now defining a number capital M as maximum of this number 1 plus norm x bar and norm xk for k less than capital N. That means norm x1, norm x2 till norm xn minus 1. Considering capital M to be this quantity, we see that norm of xk is less than or equals to capital M for all k is equal to 1, 2, 3 and so on. And this proves that the sequence xk is bounded. Now after deriving this result, let me ask you a question, that is the reverse of this result, that whether every bounded sequence is convergent. The answer for this question is obviously negative, that not all bounded sequences are convergent. For example, take the sequence xk as the first component as minus 1 to the power k and the second component is 1 upon k. This sequence of points in R2 is evidently bounded because we have norm xk as under root of 1 plus 1 upon k square, which is less than equal to 2 for every k, and hence this sequence xk is bounded, but it is not convergent because one of its component sequence, the first component, is not convergent. Now next let me move to a result that connects the concept of limit point of a set with a convergent sequence. It states that if P is a limit point of a set capital S in Rn, then there exists a sequence Pk of distinct elements in set capital S, so that this sequence Pk converges to the limit point small p. I will not prove this result. A detailed proof of this result can be found from page number 48 of the famous book Principles of Mathematical Analysis by Walter Rudin. Rather, I will give you a geometrical sketch of the proof of this result so that you can sense how to construct a sequence of distinct elements pk in capital S that converges to the limit point small p. Let's suppose the set capital S is the collection of elements inside this region excluding the boundary of this region. And suppose the location of the limit point small p is somewhere over here. Then according to the definition of limit point of a set corresponding to every given radius delta greater than 0, you consider an open ball centering at the limit point p. You will certainly have an element inside the set capital S as well as that is inside this open ball centering at the limit point small p, and this element is different than the center of this open ball. That means there exists an element P inside the intersection of capital S and the punctured disk, the open ball, having radius delta whose center has been deleted. Now this phenomenon will happen for every given delta greater than 0. Then let us consider first delta is equal to 1. Then corresponding to this delta is equal to 1, there certainly exists a point say P1 inside the set capital S, and as well P1 lies in the open ball having center P with radius 1 but whose center has been deleted. So inside this 1 radius ball you will have a point say P1 located somewhere here. Now I vary delta is equal to 1 to delta is equal to half. Then corresponding to delta equals to half you will find a point say P2 inside the intersection of capital S and this open ball having radius half whose center has been deleted. So inside the open ball having radius half you will get a point P2 somewhere here. In general, for any given natural number k, I consider delta is equal to 1 upon k, and you will find a point pk belonging to the intersection of capital S and the ball with radius 1 upon k, and now you collect all these elements p1 p2 till pk and so on. You will get a sequence pk of elements in S, for which we see that norm of pk minus p is less than 1 upon k, which converges to 0 as k tends to infinity, and hence this sequence pk converges to the vector p, and pk is a sequence inside the set capital S. In order to make the elements of the sequence pk's distinct, we need to choose p1 so that it lies inside the 1 radius ball but outside the half radius ball. You need to choose p2 such that it lies inside the half radius ball but it lies outside the 1/3 radius ball, and so on. So in this way you will get a sequence of distinct elements in capital S that converges to the limit point small p. These are all about 4 basic results on convergence of a sequence. Now we notice that to check convergence of a sequence we need to have a guess about the limit x bar. Without having a guess of the value for x bar, we cannot move for verifying this inequality for convergence of a sequence. Now here a question comes, is there any other means by which without knowing x bar we can check the convergence of a sequence? Yes, there is a way out with the help of the notion called Cauchy sequence. By a Cauchy sequence, we mean a sequence xk whose elements come arbitrarily closer to each other after certain index number. This arbitrary closeness of any pair of elements of the sequence xk is measured by assigning an arbitrary distance, say epsilon, corresponding to a given arbitrary distance epsilon. If there exists an index number capital N such that after this index number capital N you pick of any two indices m and n, you will find that the distance between xn and xm is less than epsilon. This notion of Cauchy sequence is named after the great mathematician Augustin Louis Cauchy. There is a fascinating result regarding Cauchy sequence and convergence which states that a sequence xk in Rn is convergent if and only if the sequence is a Cauchy sequence. I will not prove this result. A proof of this result can be found from theorem 3.11 on page 53 of the same book, Principles of Mathematical Analysis by Walter Rudin. However, the forward part of the proof proof is very simple to realize, because if the sequence xk is convergent and converges to x bar, then we all know for any given epsilon greater than 0 there exists an index capital N for which norm of xk minus x bar is less than epsilon, or say epsilon by 2 for all k greater than equals to capital N. Now you consider any two indices m and n. After the index capital N, you will find that the norm of xn minus xm is less than equal to, by the triangle inequality, xn minus x bar norm plus norm of xm minus x bar, which is less than epsilon. And hence it proves that a convergent sequence is certainly a Cauchy sequence. But for the reverse part, a Cauchy sequence must be convergent. We commonly require a notion called subsequence of a sequence. By a subsequence of a sequence, we mean the following. Let we are given a sequence xk in Rn. Now consider a sequence of natural numbers, say Rk, that is strictly increasing. That is, for any given k, we have rk plus 1 is strictly greater than rk, and here all the elements in rk are natural numbers. Then the sequence xrk is called a subsequence of the sequence xk. The term subsequence is due to the observation that the collection of elements inside this sequence xrk is an ordered subcollection from the elements in xk. Now let me consider a few examples for subsequences. Let us consider the sequence say xk having two components. The first component is cosine k pi and the second component is 1 over k plus 1. And consider two sequences of natural numbers that are strictly increasing. Take rk is equal to say 2k minus 1. Also take one more, say tk, given by 2k square. Then the sequence xrk, whose elements are given by xrk is equal to, the first component is cosine 2k minus 1 times pi, which is equal to minus 1, and the second component is 1 by 2k minus 1 plus 1, so it is 1 upon 2k, is a subsequence of the sequence xk. Similarly, xtk given by xtk is equal to 1 and 1 over 2k squared plus 1 is also a subsequence of the sequence xk. Now regarding convergence of a subsequence of a convergent sequence, we have the following result, that if the sequence xk is convergent and converges to some vector say x bar, then any subsequence of xk is convergent and converges to x bar. This is very easy to perceive. I am keeping this proof as a homework. From this result, we can also quickly figure out the following result, that if we get a sequence, if there are two subsequences of a sequence for which those two subsequences converge to two distinct limits, then obviously the parent sequence is divergent, because had it been convergent, then any of its subsequence must be convergent and converging to the same limit. So as a note, I will just state this observation: if there exist two different subsequences of a given sequence xk which converge to two distinct limits, then the parent sequence xk is not convergent or divergent. Now I will wrap up this portion of subsequence by mentioning the famous Bolzano-Weierstrass theorem, which states that every bounded sequence in Rn must have a convergent subsequence. We have earlier seen that a bounded sequence need not be convergent, but this result states that a bounded sequence must possess a subsequence that is convergent. This result is due to a Bohemian mathematician, Bernard Bolzano, who proved this result as a lemma in the proof of the intermediate value theorem for a continuous function. Sometime near the year of 1817, the same result, after about 50 years, was proven by a great German mathematician, Karl Weierstrass, who is now known as father of modern analysis, and thus this result is named after both the mathematicians Bolzano and Weierstrass, and famously known as Bolzano-Weierstrass theorem for a bounded sequence. For a proof of this result, you may please visit theorem 3.6 on the same book by Walter Rudin, entitled Principles of Mathematical Analysis. Now next I will move towards the concept of limit superior and limit inferior for a sequence in R. These limit superior and limit inferior are respectively supremum and infimum of the set of all subsequential limits of a given sequence of real numbers. To discuss the ideas of limit superior and limit inferior, let us start our discussion with a given bounded sequence of real numbers, say xk. Then by Bolzano-Weierstrass theorem, there is a convergent subsequence of the sequence xk. Let us suppose S be the set of all subsequential limits else of the sequence xk. That is, capital S is the collection of all real numbers else for which there exists a strictly increasing sequence of natural numbers, so that the subsequence xrk converges to the number L. By Bolzano-Weierstrass theorem, as xk has a convergent subsequence, the set capital S is non-empty and as well as bounded. Since the sequence xk is bounded, so the collection of all subsequential limits of the sequence xk is certainly bounded. Once the set capital S is bounded, it must have a least upper bound as well as a greatest lower bound. We will show that the least upper bound and the greatest lower bound of capital S are also elements of the set capital S. To realize this, let us try to visualize the locations of the elements in the set capital S. We note that the set capital S consists of those real numbers small l's for which we have a subsequence of xk that converges to the number L. So if we locate the locations of the elements in xk, we will find that wheresoever there is a gathering of the elements, there is a clustering of the elements, there is a subsequential limit. So if these points are the elements in xk, then here is a location of an element of capital S. Here is also a location of an element in capital S. Here is also a location of an element of capital S. Wheresoever there is a clotting, gathering or clustering of the elements in xk, therever you will get a subsequential limit of the sequence xk. Now as the sequence xk is bounded, there exists a lower bound of xk as well as an upper bound of xk. Then certainly the collection of all the subsequential limits L dash, L double dash, L triple dash and so on is also bounded by small m and capital M. Now there can be two possibilities, that capital S consists finitely many elements or capital S consists infinitely many elements. If capital S is a finite set, then certainly the least upper bound of capital S is nothing but the maximum most element of capital S, which is surely belong to the set capital S. If however capital S is infinite, we do not know whether the least upper bound of the set capital S will belong to the set capital S or not. But certainly capital S being bounded, there exists a supremum of the set capital S. Let us suppose x star be the supremum of the set capital S. We will prove that there exists a subsequence of xk that converges to this x star. To realize this, let us try to analyze the elements in the sequence xk that are nearby to the point x star. Let's suppose x star is located over here, and as x star is the supremum of capital S, there exists an element. As x star is the supremum of the set capital S, if we consider an element smaller than x star, let's suppose we consider x star minus 1, then there certainly exists an element in the set capital S which is bigger than x star minus 1 and less than x star. Let's suppose the location of L1 is somewhere over here. Now note that L1 is an element of the set capital S, and therefore L1 is a subsequential limit of the sequence xk. Therefore in every neighborhood of L1 there exists infinitely many elements of the sequence xk, because L1 being a subsequential limit is obviously a point of clustering or a point of clotting of the sequence xk. So if I consider a small neighborhood of L1, say this neighborhood for which this left end point is strictly bigger than x star minus 1, then inside this neighborhood there exists infinitely many elements of the sequence xk, and all the elements inside this neighborhood are then bigger than x star minus 1. Choose one of the elements of the sequence xk inside this neighborhood. Let's suppose this element is xr1 for some natural number r1. Then xr1 is such an element that is bigger than x star minus 1. Now next let us consider the location of x star minus half. Again, as x star is the supremum of the set capital S, there exists an element L2 in capital S that is bigger than x star minus half. Let's suppose the location of L2 is somewhere over here. Now as L2 is an element of capital S, there exists a subsequence of the sequence xk that converges to L2, and therefore whatsoever neighborhood of L2 you consider, inside that neighborhood of L2 there exists infinitely many elements of the sequence xk. We consider a very small neighborhood of L2, so that this neighborhood lies in between x star minus half to x star, and inside this neighborhood there exists infinitely many elements of the sequence xk. Choose an element of the sequence out of these infinitely many elements of the sequence. Let's suppose the element xr2, where R2 is such an index that is bigger than R1. This is certainly possible because here you have infinitely many elements inside this neighborhood. As there are infinitely many elements of the sequence inside this neighborhood, there certainly exists one index R2 for which R2 is bigger than the earlier index R1. So there exists R2 bigger than R1, such that xr2 is bigger than x star minus half. Now in this way there exists rk which is bigger than rk minus 1, bigger than r2 bigger than r1, such that xrk is bigger than x star minus 1 upon k. And also notice that all these elements xr1, xr2 till xrk are all less than this x star, and hence for every natural number k we get xrk that satisfies x star minus 1 upon k less than x r k less than or equals to x star, and therefore by sandwich theorem we get a subsequence xrk that converges to x star, and this subsequence xrk is a subsequence of the sequence xk, and therefore x star is also a subsequential limit, and hence this x star is belonging to the collection of all subsequential limits, the set capital S. So we get that this x star is the greatest subsequential limit of the sequence xk. This greatest subsequential limit is called the limit superior of the sequence xk and denoted by limit upper bar of the sequence xk, or also written as lim sup of the sequence xk. If we are feeling uncomfortable, then we can also place k tends to infinity on the down of the shorthand lim sup. Now in the same manner of proving x upper star an element of the set capital S, we can also prove that the greatest lower bound or infimum of the set capital S is also belonging to the set capital S. This greatest lower bound of the set capital S is called limit inferior of the sequence x k and denoted by limit lower bar xk, or by the shorthand lim inf k tends to infinity xk. Now these definitions of limit superior and limit inferior are defined for a bounded sequence xk. We note that we started our discussion with the assumption that xk is a bounded sequence of real numbers. If xk is bounded below but unbounded above, then we can define limit inferior as we have defined over here, but limit superior is defined to be positive infinity. If xk is unbounded above, we define limit superior of xk as positive infinity. Similarly, if xk is unbounded below, we define limit inferior of xk as negative infinity. Let us now consider a few sequences in which limit superior and limit inferior will be identified. Here, before going into examples, let me also inform you that this limit superior is also referred as upper limit of the sequence, and limit inferior is also referred as lower limit of the sequence xk. Now let me consider the sequences. Say xk is equal to minus 1 whole to the power k times 1 plus 1 upon k, where k is a natural number, and consider xk is equal to, say, simply k square. For this sequence, you please try to locate the locations of the elements of the sequence xk in the real number line. You will find that there are precisely two locations, minus 1 and 1, at which the sequential elements are gathered, and hence you have precisely two subsequential limits of the sequence xk, those are 1 and minus 1, and therefore limit superior of the sequence xk is equal to 1, and limit inferior of the sequence xk is equal to minus 1. But for this sequence xk, we see that this sequence is bounded below but unbounded above. As it is unbounded above, the limit superior of xk is equal to positive infinity. But we see that for limit inferior to identify, we have the set of all subsequential limits, an empty set. For such a case where the sequence is bounded below and unbounded above, but there does not exist any subsequential limit of the sequence, then we define the limit inferior of the sequence xk is also equal to positive infinity. This is just a convention. Let us write it out over here, that if xk is bounded below and there does not exist any subsequential limit of the sequence xk, then we define limit inferior as positive infinity. Similarly, if xk is bounded above but there does not exist any subsequential limit, then we define limit superior as negative infinity. Now I will state a result regarding convergence of a sequence with the help of limit superior and limit inferior, which states that a bounded sequence of real numbers is convergent if and only if its superior and inferior are identical. To prove this result, we need an observation regarding limit superior and limit inferior. Let's suppose we are given a bounded sequence of real numbers xk, and let us suppose x upper star is the limit superior of the sequence xk. Then if we try to see the location of x star among the locations of the sequential elements xk's, then we will see that x star is located at a location where x upper star is the maximum most among the gathering locations of the sequence xk. Now let us try to analyze the entire sequential elements and especially these gathering location of x upper star. Let us consider an expanded or zoomed version of this particular location. Here is the location of x star say, and inside every small neighborhood of x star, let's suppose x star minus epsilon to x star plus epsilon, then we see that outside this x star plus epsilon, that means some location somewhere over here, let's suppose x star plus epsilon, here is x star minus epsilon, then outside this level there is only a finitely many elements of the sequence. Indeed, there are finitely many elements of the sequence. There cannot be infinitely many elements lying outside x star plus epsilon, because if there are infinitely many elements outside x star plus epsilon of the sequence xk, then there are infinitely many elements outside x star plus epsilon and below an upper bound of the sequence xk. As this collection of elements of the sequence xk is an infinite collection of elements of the sequence xk, and it is a bounded infinite collection, and therefore there will exist a subsequential limit of the sequence inside this region. But this is not possible because x star is the maximum most subsequential limit of the sequence xk, and therefore outside this x star plus epsilon, that means on the right of x star plus epsilon, there is only a finitely many elements of the sequence xk. Or in a reverse way, all the elements of xk except only a finitely many elements are lying below x star plus epsilon. So for any given epsilon greater than 0, there exists a natural number n such that xk is less than x star plus epsilon for all k greater than equals to capital N. Now let us try to figure out how many elements are there that are on the right of x star minus epsilon. We see that x star being a subsequential limit of the sequence xk, there are infinitely many elements in between x star minus epsilon to x star plus epsilon of the sequence xk, and therefore xk is bigger than x star minus epsilon for infinitely many k's. This is a very important fact about an upper limit. Now I would request you to write a similar fact for the limit inferior or lower limit of the sequence xk, or rather let me write out and you try to figure out why. Now the first, this fact and this fact for upper limit and lower limit of a sequence will immediately prove that a bounded sequence xk is convergent if and only if the lower and upper limits are identical. Please try to write out the entire proof for this result, and after writing it out, please try to verify it with a proof may be found in the theorem 5.14.1 on page 162 of the book entitled Introduction to Real Analysis by Professor S.K. Mapa in its 6th edition. You know, these notions of limit infimum and limit supremum can also be defined without seeking the help of the concept of subsequential limits. These can be done in the following manner. Let me state out this manner as a result which states the following, that let's suppose we are given a bounded sequence of real numbers xk. Then we define two sequence of real numbers capital Mk and small mk, defined by capital Mk as the supremum of all the sequential elements after the kth element xk, xk plus 1, xk plus 2, and so on. The supremum of all these elements does exist because the sequence xk is assumed to be a bounded sequence. Similarly, define small mk as infimum of xk, xk plus 1, xk plus 2, and so on. Then we see that this sequence capital Mk is certainly a monotone decreasing sequence and Mk is monotone increasing. Try to figure out why. This is very simple to figure out. Now you notice that the sequences capital Mk and small mk are bounded because the sequence xk is bounded, and we all know that monotone sequences have definite behavior, that they either converge if they are bounded or they diverge to infinities if they are unbounded. As capital Mk is monotone decreasing and bounded below, certainly capital Mk is a convergent sequence. We can show that the limit of capital Mk is nothing but limit superior of the sequence xk. That means limit superior of the sequence xk can also be defined by limit k tends to infinity of capital Mk, which is supremum of all xn's for n greater than equals to k. Similarly, limit infimum xk is the limit of small mk, which is limit k tends to infinity infimum of all xn's where n is greater than or is equal to k. The proof of these two results are not straightforward. As a proof of the result, you may please visit the theorem 2.49 on page 56 of the book entitled Foundations of Mathematical Analysis by one of the giants in complex analysis, Professor Saminathan Panuswamy from IIT Madras, from Department of Mathematics, IIT Madras. I now end up the lecture here, but as usual, like the previous lectures, I will give you a few home tasks in terms of asking a few questions. The first question that I would like to ask you is the following. Let's suppose we have a sequence of points in Rn that converges to the vector x bar. Then can we ascertain that norm xk, this sequence of real numbers, converges to norm of x bar? As a second question, let us consider two sequence of points in Rn, say xk and yk, and a sequence of real numbers, say beta k. Those are such that xk converges to x bar, yk converges to y bar, and beta k converges to, say, beta bar. Then can we prove that limit of xk plus yk is equal to addition of the vectors x bar and y bar? Can we also prove that limit xk minus yk is equal to x bar minus y bar? And the third, can we show that limit beta k times xk is the vector beta bar times x bar. I will give you two more questions. The third, show that the set capital S of all subsequential limits of a bounded sequence is a closed set. By a subsequential limit of a sequence we mean a number L for which there exists a subsequence of the sequence xk which converges to the number L. This word subsequential limit I have also used during the discussion, but I forgot to mention what is a subsequential limit. Now the proof for this result is not straightforward. I would rather request you to visit theorem 3.7 on page 52 of the book Principles of Mathematical Analysis by Walter Rudin. The last question for this lecture is try to check if the sequence of points of the type 1 upon k as the first component, the second component as 1 plus minus 1 to the power k is a Cauchy sequence. With this question I stop the lecture here. In the next lecture we will consider to discuss a measurement of how rapidly a sequence xk converges to its limit, say x bar, where the notion of order of convergence of a sequence will be discussed in detail. Well, I stop the lecture here. I thank you all for all of your kind presence.